All right, so this video is going to describe how we can quantitatively describe the rate of a reaction with a rate law and how we can determine experimentally how the reactants are impacting on the rate of a reaction. So every rate law for a chemical reaction is going to be described as rate equals a constant K, which is specific at a given temperature for that reaction and has to be determined experimentally, but it's just a constant. And then that is going to be multiplied by the concentration of your reactants raised to whatever exponent, whatever order they are impacting on that reaction's rate. So for this particular reaction, because there was only one reactant, you only see that one reactant included in your rate law expression. But if your reaction had two reactants, you'd have both listed after K. If you had three, you would have three different reactants. But both the rate orders and the rate constants have to be determined experimentally. The rates are determined by looking at the instantaneous rate, basically what is present initially, um, and looking at just a brief time difference and what you started with and what would be present after that period of time. If I wanted to know the overall reaction order and I had more than one reactant, I would add all of their orders, all of the exponents for the different reactants present in my rate law together to get the overall reaction order. So in the example that I've given you, H2SeO3 has an order of 1, H plus has an order of 2, I minus has an order of 3. Those three exponents get added together to give you an overall reaction order of 6. So here in this reaction, we have chlorine and chloroform forming hydrogen chloride gas and carbon tetrachloride. And you were told the rate of your reaction is KCl2 squared CHCl3. I want to know the orders of the reactants, the overall reaction order, and the units for K. And you're given some information about the units of measurement in this rate law expression. The orders, the exponents, have to be determined experimentally because not every reaction occurs in a single step. Those are known as elementary step reactions. And at that point, the orders would be the stoichiometric ratios. Again, we're going to get into that more in the rest of our kinetics unit. But because every reaction has a step that typically slows down how quickly that reaction can occur, the orders are going to be influenced by that slow step. So the order with respect for chlorine would be its exponent, which would be 2. The order with respect to chloroform would be 1, since I just have one chloroform concentration present in my rate law expression. If chloroform had not been present, it would have an order of 0. Or if chlorine had not been present, it would have an order of 0, because anything to the 0 is 1. Again, you will not have orders for your products because they are being formed. They are not influencing how long it takes to reach that transition state. The overall reaction order would be the sum of the orders of these components, 2 plus 1 giving me 3. And then to find the units for K, we will do this mathematically as well in terms of solving for the quantity of K, but I just wanted to give you a chance to practice how you will get the units. K's units will vary. It really will depend on how much you have with respect to the orders for your reactant concentrations. So since concentration was in moles per liter, that's just big M, and your units of time were in seconds, rate is a change in concentration over a change in time. So its units would be molarity per second. The units of the reactants are going to be in concentrations. That's why we have those in brackets. And so if we know what the units are for rate, and if we know what the units are for our two reactant concentrations, we should be able to use the unit analysis to determine what the units are for K. To isolate K, we would need to bring meters cubed over to the left side of our equal sign. One of the meters would cancel out. On the left side, they would all cancel out on the right side. And so you would be left with 1 over seconds divided by meters squared, which is the same as saying 1 over meters squared second, or m to the negative 2, s to the negative 1. We're going to look at this now more quantitatively by seeing how concentration can impact on the rate of a law of reaction. And so we call this method the method of initial rates. Basically, we take initial concentrations of our reactants and we see what the rate would be initially after those reactants are allowed to combine together. With that information, we're going to need to use good experimental design, because if you write a rate law expression for the reactants that are present in this reaction, we have two of them, I minus iodide and S2O8 2 minus. So you have two unknowns. You have the order of I minus and the order of S2O8 2 minus that we need to determine. We can often just write the rate constant as K. Initially, if you wanted to solve for the numerical value for K, you would again have to know the orders of I minus and S2O8 2 minus. So why do I say experimental design is going to come into play? If you have two unknowns, you have to find a way to isolate one unknown from the other. And what I've given you here in this data table are 5 sets of concentrations and 5 sets of initial rates. I'm asking you to find the rate law, calculate the rate constant, and then determine what the initial rate would be when I minus is 0.06 and S2O8 2 minus is initially 0.015 molar. So if I compare two of these sets of data to one another, if you only have one reactant change, you can basically cancel out the other reactant, and then you would only have one unknown. So if I go back to experiments 1 and experiments 2, we see that I minus is changing, but S2O8 2 minus is not changing. So if all I do is examine experiment 1 versus experiment 2, whatever change in the rate is seen would be due solely to I minus, since S2O8 2 minus is acting as a constant. So we always want to try to pick a pair of reactions where only one of our reactant concentrations is changing, so that we don't have to worry about the other one at all. And if you look at these reactions, because K is present in both expressions, one's in the numerator, one's in the denominator, when I set these up as ratios, those K's would cancel out as well. And so that's the only piece I'm going to show you in this first example here, where I compare I minus using trials 1 and 2. I'm just going to use the concentrations of I minus changing and compare them to the rates as they change, since the Ks and the S2O8 2 minus concentrations are remaining constant. And anything raised to the m divided by anything raised to the m would just be the two values raised to the m. So when I solve this through mathematically, I would get roughly 2 to the m to be equal to 2. And we know that anything that is equal to itself would have to be raised to the first power. If these were not exact like they are here, you could use logarithmic relationships or natural logarithmic relationships to isolate m. And we will do that a little bit with lab. We're not going to have to do that too much with your experimental data. For S2O8 2 minus, you can look to see if there is a pair of reactions where S2O8 2 minus is changing and I minus is not. If there was not a pair where that was happening, because we now know the order with respect to I minus, we can just substitute that in. We only still would have one variable that we would need to solve for. I do think, however, experiments 1 and 3 are going to allow us to explore S2O8 2 minus's impact on the rate of our reaction. It's changing there while I minus is staying constant. So when I do that and compare those two quantities to one another, I get that the order again with respect to S2O8 2 minus is going to be 1. I promise your orders will not always be 1. They could be 0. It could have no impact on the rate. The rate would not change. It could be 2. It could also be a fraction. So don't just get married to whole numbers for these orders. We really have to explore how they are impacting on the reactions rate. So at this point, we now know what our orders are for I minus and S2O8 2 minus. So we know the value of M, and we know the value of n. If we want to find what the value is of our rate constant, we should be able to use any of these 5 experiments to solve for k. And I will tell you, it does not matter which one you use as long as you are consistent. So I chose to use the 5th one. But whether you use the first row, second row, third row, or fourth row of data, as long as you substitute everything in correctly and you isolate k, you'll get the same value. I did 2 significant figures because the concentrations of my reactants were to 2 sig figs. How did I get the units for K? Um, on the right side of my equal sign, I have a molarity times a molarity, which would be molarity squared. If I divide molarity squared into both sides, like we did with that first problem when we solved for units with K, one of the m's would cancel, but not the other. And so you would have 1 over seconds divided by molarity. So you can write the units as 1 over m times s, or m to the negative 1, s to the negative 1. The final piece of this was to find what the rate was when you used concentrations that you had not previously tested. If you want to find a new rate, you do have to have the value for K, which we now do have, 3.9 times 10 to the negative third. Our concentration of I minus was 0.060. The concentration of S2O8 minus we wanted to test was 0.015. And when we do our math through, we get that the rate for this particular combination of reactants would be 3.5 times 10 to the negative 6. And I have no idea why I put the slash between the negative 6 and the m. I will be moving that slash over. It should be m per s. So this second problem is a lot like the first problem. You have 3 different reactants that you are looking at. We're going to determine the orders with respect to each of those reactants, the overall reaction order, and just the value of the constant K. So again, no matter which set of reactants we want to look at, we want to find what M, N, and P are. But we want to pick a pair of experiments that hopefully we only see one reactant changing and the other staying constant. And if I'm taking a look at my data, it looks like between 1 and 4, that would work really well for ClO3 minus. It looks like between 1 and 2, that would work really well for H plus. And it looks like, sorry, I'm debating about this last one with Cl minus. Looks like 3 and 4 would work really well for Cl minus. I typically set these up so that the higher concentrations, the larger rates are in the numerator. So it doesn't matter which way you set them, but I like to have values greater than 1 rather than fractions when I do my divisions. So in this first one, when I compare experiment 4 and 1 to one another, I'm going to put 4 over 1. So I see that the concentration of ClO3 minus is 0.4 in experiment 4, but 0.2 in experiment 1. Cl minus and H plus and the constant K cancel out because they're all the same. And I set those equal to my rates, the 3.2 to the negative third and the 1.6 to the negative third. When I solve my math through, I get that my order with respect to ClO3 minus is 1. I'm going to do the same thing for Cl minus. Again, I'm going to look at 3 and 4. This one is set up good to go, so I just do 0.4 over 0.2, and I set that equal to 6.4 over 3.2 times 10 to the negative third for both values. And I get again that my order is 1. Again, I promise the orders are not always going to be 1. And then finally, I have H plus. This time I would do 2 over 1. And I do think you're going to see a different order this time. I think this time we're seeing that H plus has a greater impact on the rate of our reaction, that the order with respect to it is 2. So my rate law expression would look something like this: K times ClO3 minus times Cl minus times H plus squared. Because the orders of ClO3 minus and Cl minus were 1 each and H plus was 2, the overall order would be 4. Again, I can use any of my 4 experiments to solve for the value of K. So if I substitute in for experiment 1, my initial rate and my initial concentrations, make sure you square H plus's concentration since that was the order with respect to H plus. You would have molar to the 4th on your reactant side. And so when you bring that molar to the 4th over on the left side of your equal sign, You would cancel out 1, which would leave you with 1 over s over m cubed, or m to the negative third, s to the negative 1. And the value of the rate constant would be 1.